Hello everyone, today I would like to talk about this blinking contraption in front of me. Believe it or not, this is a computer. Now, I know what you're thinking. It does not look like a computer. Well, trust me, it is. It's got a microprocessor, which is executing instructions from a ROM chip, and the microprocessor is writing data onto its data bus, which is being read by a peripheral interface adapter, and it's spitting out the signals onto these LEDs. I mean, that's the most basic way that this thing works, but let me explain a bit more detail. But first, I need to grab it. And maybe... Yeah, there we go. Oh my goodness, there's some tape on the back of this that's going absolutely haywire. Okay, so let's turn off these annoying lights and start explaining how this thing works. So, the actual program that this thing is running is stored onto this chip that I'm pointing at. This is called a ROM chip. The way it works is that it has data programmed into it, and it cannot be manipulated by the microprocessor. It has to be put into a special programmer for the data to be manipulated. But that data will stay on the ROM chip if it's powered off. So it's good for stuff like game cartridges. Back before any of my viewers were probably born, in the 1980s, their game consoles did not use CDs, DVDs, or have games programmed into their memory. They used game cartridges, which was basically just a ROM chip on a breakout board, which would plug into a slot in the game console. And you would power it up, and your game would be on. And that's how this computer works. The ROM chip over here is basically just a very bad game cartridge. And now I'd like to talk about the processor that is doing all the magic. So first of all, let's get into the light. So hopefully you can see it. According to the very low contrast label on there, if I can get this. Well, just trust me. It is a W65CO2S. And this microprocessor is kind of special. Although, it's not really special in terms of its hardware. It is very special in terms of its history. This was the microprocessor that jump-started the home computer revolution in the 1980s, and versions of this chip made it into all sorts of different computers and game consoles. And this chip that I have right here, it is not new old stock. It isn't even old stock. This chip is still being manufactured today. Well, the original 6502 isn't manufactured today anymore because the company that made it went out of business in the mid-1990s. But the company that makes this, which is Western Digital, is still alive and well today, and they have an entire website where you can read about this chip and its corresponding components, like the peripheral interface adapter. This one over here is not made by Western Digital. It's actually made by Rockwell Semiconductor, and although it is a different brand, it's still pretty much the exact same. It has the exact same pinout, and that's all the similarities I can guarantee of. But since it works with the program that is that was written for a different peripheral interface adapter, and this thing works with it. I'd say it's pretty much the same. Now let's talk about this little chip over here. All this is a quad NAND gate, and it would take me an eternity to explain what that means. But basically, it just helps the never mind, this will take me too long to explain. So now let's turn it on and see what happens. So when you first turn it on, the program doesn't run. All that happens is the LEDs go on. You have to press this button for the program to start. There we go. And you cannot stop the program since this loops, as you can clearly see with the LEDs. And this button right here is the reset button, and it goes through, it's tied high through a 1 kilo ohm resistor over here, and it connects to the reset line on the microprocessor and the reset line on the peripheral interface adapter, because this peripheral interface adapter, and pretty much all of them, at least I think all of them, are made up of nothing but a bunch of different registers, and in this context, a register is a circuit that stores a single unit of data. Not a bit, but whatever, a certain number of bits. In this case, all of the registers that are buried inside of these two chips are 8-bit. And this reset line just goes to all of them to reset them. And the reason that the reset button needs to be pressed is for everything to start working correctly. All of the registers have to start with 0, but when it powers up, the registers all have garbage in them just for the nature of the mighty SR latch, the core of any register, and just the weird nature of it. Now let's talk about the power supply. I actually built a cable to allow you to use any sort of USB power supply with it, but I decided to use this one for this test because, well, I'm not totally sure why, but the reason that I used a USB cable for the initial test instead of this was because I have another one of these power supplies, and here it is. It looks pretty much the same until you zoom in on the 5-volt regulator. See how there's a little bit of a gray ring around one part of the area, and how some of these capacitors and such have darkened a bit? Yeah, this chip was literally on fire. Literally, there was a flame coming out of it. And you can tell by its neighbor over here, which is a 3.3 volt regulator, that this one certainly was on fire and this one wasn't, because these voltage regulators are notoriously bad. They cannot handle 12 volts. Well, at least they can't handle my 12-volt power supply, which outputs 2 amps. And this, the power supply that the computer is connected to, that's running my still functioning one, is 9-volt 1 amp, and it can deliver less than half the power of the other one, which is okay for this task since this computer isn't really consuming all that much power because of its laughably low statistics, or its laughably low capabilities. But this one over here, the 12-volt power supply, first burned out the regulator, which created an internal short in it, which caused it to get hot, and eventually for the dye inside of it to start glowing, which eventually set the packaging material on fire, which eventually told me that I needed to unplug the power supply as soon as possible. And this power supply is dead. If I hook it up to the thing and push the button, you can tell it's dead. The light isn't even coming on. Contrast to this one, where if you push the button, the light does come on. So that's about all it for this computer. Or is it? This little circuit on the bottom is the clock generator. All computers have to have a clock to synchronize all of the functions and basically set the speed for the computer. And this clock generator over here is just a 555 timer in a simple astable configuration, which makes the output start from low and then start from 0 volts, go to 5 volts, 0 volts, 5 volts, and then on every rising edge, which is where the clock transitions from 0 volts to 5 volts, the processor and the interface adapter start executing instructions. Each clock cycle is part or an entire instruction executed. And if there wasn't any clock, then it wouldn't be able to execute instructions and the computer would be useless. In modern computers, the clock goes from 0 volts to 5 volts, anywhere between 1 billion times a second and 5 billion times a second. That is insanely fast, and this processor could not handle that at all. But that's the computers of today. If you go back to 1982, the incredibly popular Commodore 64 had a clock speed of 1 million times a second. So it's over 1,000 times slower than the device that you're probably watching this on. But, I mean, it didn't really have all that much capabilities, at least compared to a computer of today. But, it used pretty much the exact same microprocessor, and although I'm using almost the same processor as the Commodore 64 would have been using, this is running at a much slower clock frequency. And the clock probably goes from low to high maybe 100 times a second, or maybe even less. But yeah, this computer is not exactly the bee's knees, and you can tell because this section over here looks like a bowl of spaghetti, but there is still plenty of organization here. Anyway, that's about it for the computer and my burned out power supply. See you next time.